It doesn't work with this.
It works here, but not. The screen cannot. Okay. So anyway, we have confining potential. We call it Q. What does it do? We are, from a physical point of view, what we're dealing with is it can be viewed as a. Can you hear me or no? You cannot hear me without microphone.
Without microphone, no.
No.
The internet, no.
Okay, we take it. Sorry.
Yes, please.
Okay.
Mm,
Somewhere near me. Here.
yes.
Good.
And in the different places, I think. Нет, тут не нужно ничего.
That microphone too. Is it audible now?
This.
It's my pointer.
Yes.
I have a physical pointer, but notice that this is a screen of, I don't know, it's a screen, and maybe I can ruin the screen, so I have to keep a distance. Not too close. Okay, so what did I have? I have a confining potential Q. This, as I said, there is a physical model where you can think of quantum particles confined by a well. Probably you have heard of such situations. You have a quantum well. You can have, it can look like quadratic. It can look like this, a sharp drop, and constant potential inside, and outside is just a wall. So in our situation, we look at more gradual situation. We have our model could be like quadratic, well, but we have much more flexibility. We don't assume quadratic, that is quadratic. Okay, so we just have some potential, confining potential, which grows at least at some strength at infinity. And these are basically minimal requirements. Then we look at, because we want to study polynomials eventually. We study polynomials of degree up to a certain degree, and then and this degree grows and so on. So but to model these polynomials, we know that we take logarithm of the modulus. That then becomes log mod p. You understand? Log mod p is a subharmonic function. In fact, it's harmonic everywhere except near the zeros. Okay, so sum of point masses at the zeros. And then since it's subharmonic, it's natural to just study the behavior of subharmonic functions related with this potential. And we come to this problem which I call the obstacle problem here. It's a well-studied object. Obstacle problems have been studied for a long time. This particular one, okay, is very close to classical ones. So we study subharmonic functions that try to come from below, reach up to the given obstacle, but they have some we have some requirement on the subharmonic function. It cannot grow too quickly at infinity. Okay, so that's a strong requirement. In terms of the number of particles, it has to do with this quantity tau, which relates to the growth at infinity. It's basically related with the degree of the polynomial or the quantity number of particles in the model. Okay. Anyway, we continue, and I observe here that in this obstacle problem, it appears a certain domain, a closed set, in fact, a closed compact set, which we call the droplet. It's the contact set for the obstacle problem. So you try to reach from below with subharmonic functions the given function. Sometimes you reach it, and sometimes you cannot. It's so far away. So it depends, but you reach it on the contact set. And that's the contact set we call the droplet. And now I will just fix for convenience the parameter value tau to be 1. And then we look at natural assumptions. We assume that the contact set, this droplet, that is just a single component thing without islands inside or anything, no holes. Okay? It's just single component. And then the boundary, well, it's just as nice as a loop boundary like this. And you assume that this boundary is smooth enough. Okay? So in my setting, the natural assumption is that it's a real analytically smooth loop. Now you might, I remember Lapjev asked me this question, and I didn't quite understand what he asked it for, but I eventually responded. He wanted to know, okay, this is like topological assumption, so what the original assumptions on the potential should be to make sure that this is true. So I can tell you that convexity will be enough. So if the potential, this confining potential is convex, we get one component droplet without holes. Okay. Yeah. Okay. More generally, you can ask what kind. If we assume everything is as smooth as possible, then what can actually happen with this droplet? How and you can show that you get always under these assumptions that the Laplacian is positive, which means some kind of weak type of convexity. It's not really convexity, just subharmonicity. But anyway, you assume a subharmonicity everywhere, and then you get that the boundary should be basically smooth, but not everywhere. The boundary can have certain kind of singularities. And these are classified by this theorem of Sakai. And it tells you that these singularities can be either of cusp type. So here's the droplet, and it reaches out and forms a cusp. Or it can be a contact point, which basically means that it's two cusps from two sides that meet. So it's like this. Okay? Any questions? Nothing?
Maybe what?
Yes?
By kissing points.
It's like you have two cusps, one like this, and the cusp from the other side meeting, and that's so the complement tries to kiss. You understand? Okay. Now we come to the setting of this quantum setting. So we, what do? We take weights associated with the potential Q, and we do these exponentially varying weights. So and this involves a parameter which we call m. The parameter m is thought of as going to infinity. Okay, so that's it's just bigger and bigger m. We consider. And what do we want to do? We want to study, in fact, the space of polynomials of degree n inside this weighted space, this L2 space with that weight. But then you see we have two competing things. We have the degree of the polynomials, the n, and then we have the degree of this power of the weight, this parameter m. And we're going to let them go to infinity. And in fact, we will then fix this parameter tau, which I want to be 1. It will be the ratio of n and m. So we actually will want to consider n is equal to m. So this is our setting. And what is the thing in general? What's the question? Well, we have these weights. And we can just think of, we're interested in orthogonal polynomials. Do you know what is an orthogonal polynomial? It's just not just a one polynomial. It's, typically it's a sequence of polynomials. Okay? But you can also characterize a single one. Orthogonal polynomials are the ones which are orthogonal to lower degree polynomials with respect to your inner products. And that's our inner product is L2 with this rapidly changing weights, exponentially changing weights. So that's our setting. We consider P0, P1, P2. These are the monic. Do you know what is monic? Does everyone know what is a monic polynomial? No? Maybe that's the wrong question. Maybe somebody knows what is a monic polynomial. Do you know what is a monic polynomial? Maybe you're not sure. It's a leading coefficient is equal to 1. It's written. Oh, you have to look. Okay, good. Okay, so anyway, we do these monic orthogonal polynomials and observe that depending on our weight, it could be a finite sequence, maybe not going to infinite degree. Okay, and then the task, the question is to find an asymptotic formula for this degree polynomial of degree m, because I said n should be m, so that's what we're looking at. We're looking at the behavior for very large m. Can we describe how they look asymptotically? You can imagine now that you do this on a computer. The computer can, in principle, give you the orthogonal polynomial degree for a given potential Q. You can calculate, you get the coefficients of the polynomial for degree, for constants, for first linear polynomials, for second quadratic polynomials, and so on. But then as the polynomial gets bigger and bigger, more and more computational capacity is needed. And the computer cannot answer this question. Cannot say, what are these orthogonal polynomials for large m? Because, you have to solve matrix equations with 1,000 by 1,000 or 10,000 by 10,000 equations. So matrices of that size, quadratic matrices, is enormous. You cannot do it efficiently. Okay, we keep on. I will characterize, will give you the analysis of this problem from the point of view of what I call soft Riemann-Hilbert problems. So what is it? It was done by Itz and Tahtajan. Okay? I think two ex-Soviet mathematicians. Probably their names are familiar to all of you, or to some of you at least. Yes? So to formulate, I do the simplest version. You take a 1 by 2 matrix. Okay, it's just a vector. And I think of it as a row vector, not as a column vector, as standard in textbook. But okay, I try to conform with the notation, so that's and then we consider this matrix, which has lots of zeros, and one entry is non-zero. When we try to solve that, the so-called, which I call soft Riemann-Hilbert problem here, is just a d-bar problem. You take d-bar of this, so y there is a function, but it's matrix valued function of a complex variable. And everything is functions of a complex variable. And you try to solve this equation. D bar u is equal to y bar w. Now, you might start to think, okay, that's a nice equation, but it's a very specific situation here, and maybe we should solve the scalar version of the question first. You can imagine this equation 1. Think everything is scalar. W is scalar. The function, this vector y is scalar, and so on. And you think maybe it's easy. You have to rethink. It's very hard. Only numerical techniques exist here, essentially. Why is it hard? It's because this changing of complex structure. You go from it's not a linear equation, right? If it would be a linear equation, you just solve it immediately, nothing to it. But it's hard. And here we try to couple it with this asymptotics at infinity also. We want this asymptotics at infinity. Why is that the right asymptotics? I'll tell you in a moment. But you see, so we have this equation, one together, and that should be true. One should hold in the whole complex plane.
Excuse me, please. Could you recall us what is d bar?
D bar. If you have a polynomial in Z, you write it a polynomial in X and Y, two real variables. You can then write X as what is it, Z plus Z bar over 2. And you write Y as, what is it? It's Z minus Z bar over 2I. And then your polynomial suddenly becomes a polynomial Z and Z bar. And then you just think of it as the derivative with respect to Z bar while keeping Z constant. This has a formula, this is a nice formula, it's just whatever. Half times d dx plus I d dy. It's a standard complex derivative. Okay? And you do it component-wise in the vector. So nothing strange here. Okay, and then we just look at what is this problem of its Untitled. We calculate this y bar times w, and we get the row vector. 0 and p bar e to the minus, okay. On the other hand, you just take d bar, it works component-wise on the vector. So our equation, one, it's the equation that d bar of p is 0, and d bar of phi is this given expression, p bar e to the minus 2 mq. So if d bar of p is 0 everywhere, it means that the function doesn't depend on z bar, so it depends only on z, and that means it's an entire function. Okay, p is entire, but when then we go back and look here, okay, we have this condition 2. What does it say? The condition 2 means that p grows like a polynomial. And if it's an entire function which grows like a polynomial, there's no other choice that it is a polynomial. Okay? Okay, and then the second condition, it says that this function phi decays quite rapidly. And it turns out that that condition expresses that p is orthogonal to all polynomials of lower degree. So this equation, this problem, gives you a way to express the properties of the orthogonal polynomials. And that was what they hoped. So they hoped, Itz and Tatajan hoped that this would be the way to solve the problem, to find the orthogonal polynomial, the asymptotics of them. So I give you also some insights now into why you get orthogonal polynomials this way, why this condition requires you to have an orthogonal polynomial. It's because of this beautiful expansion, which is just a finite geometric series. 1 over 1 minus x, we know it's 1 plus x squared, and so on. If you cut it, you get on the left-hand side some change. You have to, but exactly this is the, could be viewed as the formula. Finite expansion. And then you implement the finite expansion, you get this, okay? Notice here that first we have coefficients times divided by z to powers, and then there's a remainder term. Now, using that expansion, you can see that the decay, that rapid decay, it means that all those coefficients have to vanish. And so you get the orthogonality to lower degree polynomials. Okay. Now I will tell you how to solve it, because that's what Itz and Tatajan did not know. And I only realized it like a couple of years ago or something, how to do it. And it turns out it's quite easy. Just have to make the right moves. So our Ansatz. Ansatz is a German word. Maybe it exists in Russian also. Ansatz. Предположение. Supposition, yes. Yes. But it's also used in English. So you can use, so I use it. So we take this, we take a certain constant Cm times what? We have a function phi. What is this function phi? We had, you remember I had this droplet, which was simply connected. No holes inside and compact. So what we do is we look at the complement. It's a domain, which includes infinity. It's simply connected domain. And we can map it to the exterior of the unit disk. So that infinity goes to infinity. And then we call that mapping phi. It's conformal mapping. Then I need one more function. A little bit tricky, but we solve the, first we look at our boundary loop, and we consider, okay, we'll consider our potential Q there, and then we harmonically extend it to the exterior domain. After the extension to the exterior domain, what do? We need, using, well, it's Dirichlet problem, right? We can solve the Dirichlet problem in the exterior domain. Then after that, we need the existence of a harmonic conjugate function, which we know it exists because the complement is simply connected if you add on the infinity point. And then we get the harmonic conjugate, and then we have an analytic function whose real part is the given function on the boundary curve. Okay, so that's a script Q function. All right, and that script Q is the way to build the guess for the polynomial. So the ansatz looks a little funny. It looks, you take a constant times phi to the power m, but phi, by the way, grows like linearly at infinity. It's like constant times z at infinity. So that's good. It grows like, it behaves like a polynomial of degree m at infinity. So it has some good property. And then e to the m times script q, what is it? It's a bounded function there. So it just adapts a little bit. It doesn't change the polynomial growth behavior. And then f is a function which I throw in there, which we don't know anything about at the moment. But we want to this function to be have the property that the value to infinity is a fixed one. So and it's a holomorphic function. Now, can you see something that's somehow wrong with it? The assumptions? Nothing? No. But let me tell you first that this function phi is not well defined in the whole complex plane. The same with this script q function. So it's like a little shaky. What's going on inside this droplet? The thing is that we don't really need to worry too much about it. We just, it turns out that it's enough to worry what's happening in the exterior domain and just a little bit inside. Okay. Now we need to guess the right thing for the potential, this other, well, the phi function, which solves the Debord problem. Okay, and there it's a little more tricky. We need the error function. I use the probability error function, not the physical one. And then the guess is similar. But notice, first of all, there's a m to the negative a half somehow throwing in there, okay? And then the negative powers of phi. negative power, and negative power on the rest also. And then we have to throw in two functions. A is supposed to be holomorphic and bounded at infinity, and B is some smooth function. We need also a function V. What is V? V is some choice of square root of a function R. Now, R is defined up there. Let me try to point at it without destroying your screen. Okay, so we need this Q brev. And that function is a close approximation of this harmonic. It's a close approximation of the potential Q near the curve, the boundary curve. It's a close approximation. Sorry, it fell down. You have to, I have to find a way to. Stability is not easy. Stability of matter is a serious problem. You know? Okay. So but it's slightly below, except on this curve, where it's they're equal. So you have this the function q, it goes like this, and then the function q brev, it goes like that, and they're linearly at linear level. They are tangential there. Now you form the difference. It looks like a quadratic function near this curve, so we can take its square root, and the square root will behave like linear. So we choose a square root which is smooth, which exists. And then we choose this linear growth. So we choose V to grow in the exterior direction and fall in the interior direction. There are many square roots of, if you take x squared, you take the standard x squared, you take the brutal square root, you get this, right? Absolute value function. But I want a smooth one, so we can choose this one and then negative there. Right? X squared is x is smooth, x squared, it works. You don't have to take absolute value of x. Okay, yes, and we did this. And now, in fact, it turned out I did nothing much yet. I didn't make any assumptions on this function f and on the function a and b. Not much. But I need to fix some kind of reasonable behavior of those functions. And it turns out that it's possible to assume that f has an asymptotic expansion in 1 over m, like a Taylor series. And that a and b have such expansions as well. And the coefficients don't depend on m anymore. There are a lot of ways a function can depend on the parameter m. And this is like the simplest possible type of behavior, right? Okay, so that's what I try here, and okay, it might be false. Then to check it, we calculate the d bar. We try to solve the d bar equation after all. Now we take d bar of phi, it's that expression there after just some simple calculation. And we want it to be equal to this p bar e to the minus 2mq. And we check that that has the given form there in terms of f. So now, after these changes, the equation is quite simple. The equation looks like this equation 3. Uravnение 3. Okay. Then we just look at the curve, this boundary curve, see what is the requirement there. There, the square root is 0. The v is 0. So one term falls off. And the equation just looks like that. Now this is an equation where we can hope to get some traction. Why? Well, it starts to look like a jump problem. In fact, look, if d bar of v is 1, for instance, then it's just A is holomorphic in the exterior, F bar is conjugate holomorphic in the exterior. And it looks like A and F are the decomposition of the jump. It's how to say it? It's like solving Dirichlet problem, in fact. And more generally, you can think of it without this assumption I made on V. It's just a Riemann-Hilbert problem. Okay, Riemann-Hilbert. And we can solve it. Not very difficult. It's a scalar Riemann-Hilbert problem. It's a jump problem along this interface gamma 1. And now, how do we solve for B? Well, you see this equation here. I told you that we can think of it like it's a Riemann-Hilbert problem to get A and F out of this equation if we know B. But how to get B? Well, it turns out that the equation, we study it, the original equation is that instead of doing a restriction to the curve, we look at the equation near the curve, then we get B also. It's a division problem. So the other one was a jump problem, a Riemann-Hilbert problem. This is a division problem. And a little bit unfortunate that B, and the way to express B is in terms of this division, but look, nasty thing. On the right-hand side, there's a B too, right? Another B. Luckily, this other B is a lower order of M, smaller. So it doesn't influence so much. Anyway, we can solve this equation using Neumann series, and we get it. We get a very strong, good approximation for a B. And we get a smooth enough solution. So how these things work together? We solve the Riemann-Hilbert jump problem, and then we implement that solution into, okay, we finished soon. And we implement it into the division problem. And then we go use that new improved information, throw it into the Riemann-Hilbert problem again, and go back and forth, like a yo-yo. You have played with a yo-yo, right? As kids. So that's how it works. And this is, let's see, I should finish soon. I just tell you some things that we can move to the case of the unit circle by transfer of every coordinates, a new coordinate chart, and their equations are the same, more or less. And the solution is implemented using the Herglotz operator and projections. And then I can write down the solutions of these equations in these coordinates. And in terms of the unknown B. But then once you have that, you can also do the solution, how to get B. And it looks like this equation. And that's the one we solve using Neumann series, finite Neumann series. Okay, so yeah. So it's like a Neumann series, you just iterate. Approximate solution using Neumann series. And now the technology to see how the error terms look, that's I implement the Nishida-Nirenberg approach to study. Well, actually, it's the Cauchy-Kovalevsky problem. Similar technology methods. And final results are that we can actually get very good approximation. So we get, we see that we can approximate the orthogonal polynomial by a good approximation, which is given these terms where we cut off, we take a finite series, a finite asymptotic series, and then we cut off at the right moment, and we get not exponentially decaying errors as I hoped, but we got them like corresponding to Gevrey class dropping. So I would have wanted exponential, but it's exponential to minus square root of m in principle. That's the kind of decay we get. And here, this improves on earlier work by joint work with my former student Aron Bandman. We managed then to get the asymptotic expansion with using completely different technology, but we could not control error terms, and now we have better understanding. So here are some papers related to this topic. This joint work with Amar and Makarov. They also mention work by Karleman, which is very old, on orthogonal polynomials. There is, this paper by Itz and Tahtajan. Klein and McLaughlin, it deals with a scalar D-bar problem, which I told you was hard to solve. Then this paper by Nishida, and then also Sega, which was slightly before Karleman. How am I doing with time? It's okay? I have 1 minute. Isn't that great? So we have 1 minute for questions. Yes?
You were talking about the asymptotic formula expansion of polynomials. If you phrase it in terms of the zeros of polynomials, do they converge to something?
Most likely they converge, but this problem of where the zeros are is more sensitive, because the zeros are inside the droplet, and they some kind of mother body, but it's a very unstable question.
What about the limiting behavior? Do zeros as sets of polynomials limit go to something uniform with respect to some pressure, or it's really
No, it's not random, but okay. Typically, they accumulate to some curve, like Sager's curve, you know. But here, it's highly sensitive, because you change something a little bit, and suddenly this curve changes dramatically. So it's and the reason may be that where you have the zeros, they are in the domain where, well, there's a probability wave associated with the polynomial, and the probability wave has a ridge. It's on this boundary of the droplet. It's near there. It has like a Gaussian ridge, and inside is very flat. And that's where the zeros are. So it's highly sensitive. It's not just slight changes, and the whole picture changes, I think. And this was done, this Sun-Yup Lee, who's Korean in the United States, he did some, he wrote some preprint about it, this instability.